the second and final video in the short series on an introduction to polymer science. In the previous video, listed in the description below, we saw that polymers were essentially long molecules composed of individual monomers that were strung together. This is done by various methods and follows various kinetics, which means that any given chain can be a different length than another chain in the same batch. Therefore, there is actually no such thing as a molecular weight for a polymer, as each individual strand can be a different length. Instead, the best you can do is find some sort of an average mass within a sample. There's two ways of doing this. The simplest way is what's called the number average molar mass. As can be seen, this is just a straight up average. You add up all of the different weights and divide that by the number of chains that you have. A straight average, however, can disproportionately weight heavier polymers. Therefore, a more accurate way of calculating the average mass in a sample is what's called the mass average molar mass, which is a weighted average. In this case, the mass that has the most number of chains is the one that controls or predominates in calculating the average. Both of these are used in conjunction to essentially determine the homogeneity of a sample. This is called the polydispersity. Polydispersity index is calculated by dividing the mass average molar mass by the number average molar mass. Ideally, if all the chains are of equal length and equal mass, you'd have a polydispersity of 1. Polymers that approach 1, generally speaking, are mechanically strong and have high melting points. However, that's one of the beauties of polymer science, is that you can construct polymers for different purposes. For example, you might not want a strong plastic, you might want something flexible. In that case, polydispersities greater than 1 are soft and flexible and have low melting points. Both of these types of materials have applications. In general, radical polymerization gives you the highest polydispersity, followed by various step growth polymerizations. The most homogeneous polymers are produced by anionic polymerization and generally have a polydispersity index approaching 1. Each of the averages is calculated or determined using a different methodology. Most popularly defined the number average molar mass, one uses the osmotic pressure of a polymer solution. As you may recall, the osmotic pressure is the molarity of the solution times RT taken from the ideal gas law. This can be modified. If one measures the concentration of an unknown in simply weight per volume, kilograms per meter cubed, that concentration winds up being the number average mass times the number of particles you have divided by Avogadro's number over the volume, which will give you grams per mole, or in other words, the molarity of the solution is the concentration divided by the concentration in kilograms per meter cubed divided by the number average molar mass. So the osmotic pressure equation winds up as follows. In this case, one measurement is not possible to give an accurate result. It is generally expanded into a power series, where you have terms B, C, D as the variables get raised to the second, third, fourth power, and so on. In order to use this, various osmotic pressures at different concentrations are measured. A plot of pi divided by RTC versus C at multiple concentrations essentially gives you the equation of a line, where the power series term B winds up being the slope and 1 over the number average molar mass winds up being the intercept. So if I have a given polymer solution at 25 degrees C, for example, just using 2 points on the line. The first one has a concentration of 2.5 kilograms per meter cubed. The second one, 7 kilograms per meter cubed. The left side of the equation, pi RT over C, comes out as 0.0102 moles per kilogram for the first solution, 0.0145 moles per kilogram for the second solution. You now have simultaneous equations that can be solved where the only unknowns are the slope and the intercept. Solving these, you find out that this particular polymer would have a number average molar mass of 98.1 kilograms per mole. And the slope, the B of T term, is actually interesting. If you look at the units, it's 9.2 meters cubed per mole. This is essentially the inverse of the density of the polymer solution. The density of a polymer solution gives you a good indication of what the conformation of the polymer is, as long rods, rigid rods, take up much less space than globular polymers. Mass average molar mass is measured by a technique called light scattering. Start with, in a simple case, one generally considers a molecule as having 2 centers of mass, 2 atoms, or 2 components joined by a bond. And typically that bond is written as a straight line. However, we know that the bond is not rigid, it's flexible, and it is also made up of charged particles. So in essence, any covalent bond is an oscillating dipole as the charges move back and forth. Light is also an oscillating dipole. These 2 dipoles will interact. So when a light photon hits a molecule, it does not simply disappear. It doesn't go through. It bounces off in various different directions as the dipoles interact, giving you scattering, where the sum of the intensities of all the scattered light winds up being equal to the intensity of the incident light. How this works is essentially Rayleigh scattering. Light is dispersed spherically. So you get the following relationship where I is the intensity of light scattered at whatever theta degrees one is measuring at. I0 is the intensity of the incident light at a wavelength lambda. R is the radius of the dipole, in this case, the size of the molecule. Epsilon 0 is the permittivity of a vacuum. And alpha is what's called the polarizability of the solution. How easily is it affected by light or any oscillating dipole? The polarizability of a solution can essentially be determined by taking the squares of the indexes of refraction. The index of refraction of the solution squared, n squared, minus the index of refraction of the pure solvent squared, times the permittivity of a vacuum, divided by the number of particles in the solution. Essentially, this can be solved in a gradient solution as 2 times the index of refraction of the solvent times the change in index of refraction with the change in concentration with the mass average molar mass now included. So you get a rather long and seemingly complicated term now. In this, you'll notice most of the things in here, such as the index of refraction of the solvent, Avogadro's number, the wavelength of the light, are known. The change in index of refraction with concentration has to be measured before one runs the experiment, so various concentrations of polymer have the indexes of refractions measured. This can be related to Beer's law. which, if you recall, absorbance, the log of I0 over I, the incident light versus the amount of light that passes through the sample, is equal to a molar absorptivity times the concentration times the path length. In the case of scattering, you have incident light coming in. The majority of that light will pass through the molecule. However, part of it will be scattered. So the intensity of light passing through the molecule to the detector in Beer's law is going to be the initial intensity minus the sum of the intensity of all the scattered lights. As mentioned, epsilon is absorptivity. Absorptivity in this case is related to a term called turbidity, because the polymers are large enough to actually form particulates within the solution that scatter the light. So solving Beer's law, replacing epsilon with turbidity, you get the intensity of light that's measured is equal to the initial intensity, e to the minus turbidity times the path length of the cell. Turbidity, once again, has a long term. However, one notices that you have knowns, such as the index of refraction of the solution, Avogadro's number, the wavelength of the light you're using. Measured terms, the changes of index of refraction with concentration. The concentration, which is known, where the only unknown is now the mass average molar mass. This term, which has all of your knowns, or what would be called machine constants, such as the change in index with concentration, is simply given as a term H. So, when one measures turbidity, one can plot this H term times the concentration divided by turbidity at a given concentration versus that concentration. The intercept of this plot will be 1 over the mass average molar mass. Light scattering is an incredibly accurate and also a very meticulous process. The solvent has to be perfectly clean, has to be perfectly pure, and the sample has to be dissolved so that the scattering centers are actually single polymer chains and not agglomerations of polymers. However, once these terms are met, the method is very straightforward and gives a very accurate result. There is a third method for measuring the molar mass of polymers. This one is probably the quickest and simplest: viscometry. A viscometer is basically a U-tube, where one side of the tube is a thinner tube versus a thicker tube on the other side. The tube is filled with a solution. You notice there's 2 timing marks on it. How a viscosity experiment works is the solution is drawn up into the thin side of the U-tube through suction. Suction is released. Gravity causes the solution to fall back down, and one measures the amount of time it takes to pass between the 2 marks. The viscosity at some given concentration, basically due to the capillary action, is going to be equal to the viscosity of the solvent times the density of the solvent times the time it took the solvent to pass, the pure solvent, divided by the density of the solution at a given concentration and the time it took for that solution to pass the timing marks. Simpler, you can get a relative viscosity, where the ratio of the viscosity of the solution to the pure solvent is simply the ratio of the time measured for the pure solution to the time measured for the pure solvent. Specific viscosity is also measured, and there's a reason for these various measurements, where the time at a concentration minus the time for the solvent divided by the time for the solvent gives you the specific viscosity. These two terms are used in something called the Mark-Howing equation, where the viscosity is some constant K times what is known as the viscometry average molar mass, m sub v, to some power alpha. Two plots are required. Various measurements of viscosity are made with the viscometer at various concentrations. A plot of reduced viscosity, which is the specific viscosity divided by C versus concentration, would be one plot. And something called the inherent viscosity, which is the log of the reduced viscosity over C versus C, would be the other plot. These will have a common intercept if the solutions are properly prepared. The intercept is 1 over the viscometry average molecular weight. Viscometry is very useful because, as mentioned, it's actually a simple experiment to do, and it's also relatively quick. It is used for systems that are well understood. K and alpha are intrinsic values for any combination of polymer solvent system. This is useful in industry as there are not very many novel new polymers. Essentially, the point of polymer engineering is to take the polymers that are known and to play with molecular weights or chain lengths to get various desirable properties out of them. So viscometry can be used very quickly to analyze a system of a known polymer to see if that system will have the desired properties. In general, the viscometry average molecular weight looks a lot like the mass average molecular weight, as in it's a weighted average, except it includes this term alpha to account for interactions between the polymer and the solvent. In terms of accuracy, the most accurate average molar mass is the mass average molar mass. The viscometry average molar mass is actually a close second, which is another reason why it's a useful technique. And the simplest number average molar mass gives you the most dispersity, or the most error, if you would, in the measurements of the polymer. Again, this isn't because there's an error, it's simply because the average molar mass, the number average molar mass, doesn't account for the fact that the smaller weight polymer could be the most predominant species in the sample. Thank you very much for listening, and I hope you found this useful and enjoyable.